Welcome and good afternoon. I'm J.D. Stillwater. I'm a science teacher at the Circle School in Harrisburg, Pennsylvania, a wonderful little institution in its own right. But I'm not here to talk about Circle School today. Can you see the screen? Okay, good. I'm here to take you on an exploration of the spirituality that's inherent in science. And when I say that, I think a lot of people have in mind something like this, a spectrum where spirituality and religion are diametrically opposed to science and reason. I don't view science and spirituality as opposite ends of a spectrum. I think if there is a spectrum, this is the wrong one. For me, the spectrum lies between dogma and ambiguity, between separation and connection, between self-righteous conviction and mystery. Heated arguments between atheists and believers happen between parties who both sit on the same end of this spectrum. And I think that argument is now obsolete. So 7 Candles is an invitation to dance over here. The problem with that old view is that science refuses to keep to its end of the spectrum. It keeps revealing things about nature that conflict with our religious beliefs. And spirituality also refuses to keep to its end. For many people today, spirituality is less about specific religious beliefs and more about transformation. Spirituality as a way of becoming. So there's an emergent synthesis that's happening all over the world now, driven on one side by the incredible success of the scientific endeavor, and on the other by our basic human longings for connection and for reverence. Theologians, even conservative ones, are looking at what science has revealed, and they're recognizing a transformative story that's as powerful as Scripture. And scientists are looking around at reality from quarks to qualia to quasars, and they're experiencing a profound sense of oneness and joy and reverence, spiritual experiences. My purpose in this talk is to offer that science and spirituality are not only compatible, they're mutually enriching. Science is about knowledge. It's a process for constructing shared models of reality. Models that people from all different backgrounds can agree on. And if contradictory evidence comes along, contradicting our models, we agree to seek new models that fit nature better. Now, the important words here are we and shared and agree. Science is a communal, transparent, now global endeavor. Spirituality is both an experience and a practice. It's a transcendent feeling of being part of something bigger than ourselves, something profound, something sacred. That often happens in nature. It does for me, maybe for many of you too. Nature is a very important source of spiritual experience for many people. Spiritual practice is about transformation, about becoming our best selves within that larger context, that larger integrated whole that we find ourselves in. So spirituality underlies all the various religious traditions of the world, but spirituality is not religion. Religion is our specific beliefs and rituals. Spirituality is a universal human experience. I'm not here to sell you any new beliefs this afternoon. Seriously. Whatever theology or spirituality you came in here with, whatever worldview you bring to your life, I honor that and I respect your spiritual path and any beliefs that go with that spiritual path. 7 Candles is about how science can add to and integrate with those beliefs and the spirituality that they nurture for you. Deal? All right. When I ponder the universe as science reveals it, I experience spiritual renewal. And it's that experience I want to share with you today. I encourage you to keep your own spirituality and your religion close by and just see how they mesh with what I'm offering. The 7 candles of my title are 7 revelations, 7 illuminations from science, each potentially as profound and disturbing as Galileo's revelation that the earth orbits the sun instead of the other way around. Very disturbing to the culture and society of his time. Now, before we dive in, I just want to ask you to hold any questions until the end. And this is a reminder to all of us to silence our phones so that we can do this without the being disturbed. Are you ready? All right. First candle, scale. When we look up into the night sky, we see all these bright dots. Well, some of those dots, as you know, are the 8 planets in our own solar system. Sorry, Pluto, we do still love you, but you just don't quite measure up anymore. Some of those bright dots are stars, like our sun, 1,000,000 times the size of the Earth. But stars, the ones we call stars, are suns that are much further away, light years away. Now let's pause and make sure we understand that a light year is a unit of distance, not an amount of time. It's the distance that light can travel in an entire year. Light's really fast, so it's a long, long way. Some of those bright dots that we see in the night sky are entire galaxies of stars. Like our own Milky Way galaxy, you can see we kind of live out in the suburbs of our galaxy, and it's really, really big. But some of those the ones that we call galaxies, are ones that are much further away, outside of our galaxy, other galaxies. Here are some Hubble photographs of other galaxies besides our own. What always strikes me about these images from Hubble of other galaxies is just how beautiful they are. They're just gorgeous. Galaxies that we can see with our telescopes are millions or billions of light years away. Millions of light years away from us. From here, we can see 100 billion galaxies with about 400 billion stars in each one. That's what I used to say in this presentation. Last week, NASA did a new sky survey and released a new number about the number of galaxies in the observable universe. 2 trillion galaxies, each with about 400 billion stars on average. There are more stars in the known universe than there are grains of sand on planet Earth. It gets worse. There's about 10,000 stars for each grain of sand on the Earth. That's what I used to say. Now it's more like 200,000 stars for each grain of sand on the Earth. The numbers are so big, it almost doesn't matter. So, and just in the last few years, astronomers have figured out how to detect planets orbiting other stars. Now we're talking about stars quite close to us in our little portion of the Milky Way galaxy. And just in the last few months, their estimates have gone from about 150 billion planets in the Milky Way galaxy alone. Now they're saying there's about 150 billion Earth-like planets in our Milky Way galaxy alone. And those numbers are just going to grow as we find new ways to find these other planets. Now, when we say something is light years away, one of the implications is that when we look up, we are seeing history. Even light from our own sun takes a little over 8 minutes to reach us. So if the sun were to explode right now, we wouldn't know anything about it and we wouldn't see it happen until 4 minutes and 16 seconds later. 8 minutes and 16 seconds later. And then the image and the light and the heat would reach us all at once, and then we wouldn't know anything about it because it would just be gone. So the next closest star to us is Proxima Centauri. It's 4 light years away. So again, if there were some big event that happened in the Centauri system around Proxima Centauri, it would take 4 years for the image of that event to travel through space before we would see it happen 4 years later. Now, in the last decade, NASA has taken a series of very interesting photographs. The first one was in 2004, called the NASA Deep Field. And what they did is they picked a spot in the sky, a very small spot, in between all the known stars and galaxies. A place where the sky was completely black, as far as anyone knew. A tiny little piece of sky zoomed in, about as big as a grain of sand held at the end of your arm. So they had it on maximum zoom. And they figured if there's anything to see in that tiny little piece of blackness, it's going to be so dim that we have to open the shutter on the camera and leave it open for a long time, days or even weeks, just to gather what little bits of light might be coming in. They did that, and they closed the shutter, and they were amazed at what they saw. You want to see the image? Here's actually one of their more recent ones. This is the extreme deep field. Light from over 10,000 galaxies is captured in this image. Every little dot on here is an entire galaxy of stars. Light from some of these galaxies traveled through space for 13 billion years before finally ending its journey inside the Hubble's camera. If you want to look further away than 13 billion light years, or further back in time than 13 billion years, you can't. There's nothing to see. Because 13 billion years ago, the very first galaxies formed with the first stars. You're looking at them in this image, some of them. Now, there's this phenomenon called redshift that allows us to look at light from distant galaxies, the colors of light that come through, and determine, calculate their speed and direction relative to us. And when we do that, we find that galaxies that are fairly close to ours are moving away from us. Things that are far away are also moving away from us, and everything in between is also moving away from us. Everything is moving away from us. But the furthest things are moving away the fastest, and the closer things are moving away but not as fast. So if you make a picture of this in your mind, it's kind of like a classic explosion. Everything's moving away from us. The furthest things are moving away the fastest, right? And things in between are moving away, but at an in-between speed. Twice as far away is twice as fast moving away from us. So just for the heck of it, let's run the movie backwards. Let's, in our imaginations, ask ourselves, what happened before this? And when we do that, we can calculate those speeds and work backwards to figure out that it takes about 13.8 billion years for everything in the universe to arrive right here. Because remember, in forwards time, it's moving away from us. In backwards time, it's coming right here. Now, the universe didn't begin with a watermelon. I hope that's obvious to everyone. That's a very important distinction between this video and reality. It began with a singularity, and I'll say more about that in a little while. But there's another very important distinction between this video and reality that you might not notice at first. And that is that this watermelon exploded on a table in a field with a forest in the background. The universe doesn't take place in a setting that was already there. The universe is simultaneously the event and the setting. That's a little difficult for me to quite get a picture of in my head, so I'll say more about that in a little while too. There's no setting it takes place in. Now, there's a lot more to say about the scale of the universe, both in time and space. I haven't said anything about dark matter or dark energy, but I will say that everything we can see, everything we can take account of in today's universe represents about 4% of the total. The other 96% is this very mysterious dark matter and dark energy. I also haven't said anything about the other end of the scale, the very small. I haven't touched on atoms and subatomic particles and quarks. I'll say a little bit about that in the fourth candle. So the essence of this first candle is that time and space are vast, almost beyond comprehension. Looking out is looking back in time, and if we look far enough, we can almost see the very beginning. And given the number of planets out there, we're probably not alone. Now, some people respond to the scale of the universe in both time and space by feeling small, feeling insignificant. For me, thinking about it carries me beyond thinking to awe and a profound sense of connection with all that beauty and majesty that we can see out there. Second candle, flow. Does anybody know the compass directions in this building? Where's north? Michael's pointing this way. Everybody agree? All right. We'll pretend it's a geography quiz. Everybody raise your hand. Just play with me. Raise your hand and point towards Canada. Good. All right. How about Minnesota? Yeah, pretty sharp people in here, geographically at least. How about California? Hawaii? China? You've been here before. before. Yeah, China's that way, isn't it? Yeah, even after 500 years, our mindset is still as though the earth were flat. We know better, but we're still stuck in this sort of mind group. So here we are, about 40 degrees north of the equator, 40 degrees latitude. And I hope you'll agree that down, wherever you go on the earth, is towards the center of the earth. Is that right? So if you're in Australia, you're not upside down. For you, down is still towards the center of the earth. Got it. Down is towards the center of the earth. Unless you happen to be standing on the moon, in which case everything on the earth is up, and down is towards the center of the moon for you now, right? If you're in a spaceship in between the stars, how do you know if your spaceship is upside down? It's irrelevant. It doesn't. There is no up and down once you're up off a planet. So direction is relative. Even really simple concepts like up and down depend on where you are, depend on your location. So here we are sitting in the yoga studio. If we're sitting as still as we can, are we nevertheless moving? And if so, how fast? Huh?
As fast as the Earth is moving.
As fast as the Earth is turning, yep. 700 miles an hour, that is at our latitude. If you go down to the equator, it's more like 1,000 miles an hour. Pretty fast. So is that it? That's how fast we're moving right now, sitting still here in our church?
No, you got to add the path around the sun of the earth.
Right, we're also orbiting the sun. That's a little bit faster. But still, we could calculate. We could add the 700 miles an hour at midnight and subtract it at noon, and we could figure out how fast we're actually moving right now, right? Go ahead.
Yeah, I don't remember offhand.
There is another movement we have to take into account. Yeah.
We're moving away from the sun, right?
Sometimes we're moving a little away, and sometimes.
Moving away.
What's that?
Isn't our whole system moving away?
Yes. We and all the other stars in our galaxy are orbiting the black hole at the center of our galaxy. That's a little bit faster, as you can see. But still, theoretically, we should be able to add the 86,000 to this, subtract it at other times, add and subtract the 700 miles per hour, and we should be able to find our actual speed, right?
Well, there'd be one more, right?
What would that be?
Yes.
Because, well, we're rotating around the Milky Way, but the Milky Way is moving in itself, right? Rotationally.
Away from the singularity.
You are one step ahead of me.
Okay.
Yes, you're exactly right. The galaxy must be moving because space is expanding. We think, but we're not sure. And the reason is because everything is moving. There's nothing in the universe that's sitting still. So speed is relative. Even location is relative. Remember, if we run the movie of time backwards, everything in the universe comes back to right here. Cosmologist Brian Swing put it this way. He said, the universe does not expand into a pre-existing space. Space unfurls with the universe. It's very difficult to grasp, so let me try it a different way. Just a balloon with some stars printed on it, and the stars represent the various galaxies in the observable universe, right? What we've done in this analogy is collapse the 3 dimensions of our space-time, or 4 dimensions of our space-time, down into the thin rubber of this balloon, right? So if you want to go from one galaxy to another, you have to crawl like an ant on the surface of the balloon. You follow that? Mm-hmm. All right. We live in an expanding universe, and what that means is that space expands like this. The universe expands because space itself expands. All right? So as I blow into the balloon, let's make it a little smaller so we don't pop it. Pick a star to represent our galaxy. All right? It doesn't matter which star you pick. It could be any star on the balloon. You got one? All right. Now watch as I add air to the balloon, and you'll see that all the other stars representing galaxies move away from the one you picked. And the ones that are further away move away the fastest. All right? Watch. You see that? All right. That's That's what we see when we look out. Now, in our imaginations, let's run time backwards again. In time backwards mode, all the other stars representing galaxies are approaching the one that you picked, right? Furthest one's fastest, closest one's approaching but not as fast, until we get to the beginning of time. But the universe didn't start with a limp balloon or a watermelon. The laws of physics dictate that when you get this much stuff this close together, it collapses down into something called a singularity. That's where everything in the universe occupies no space at all, no volume, no height, no width, no depth. Everything in the universe, one thing, infinitely small and infinitely compact. A singularity. I like that word, singularity, one thing. All right, now let's begin time again. In the forwards direction. And this is where we find ourselves now in an expanding universe. And I have an obnoxious question for you. Which point on the balloon is the center of the universe? You could say, correctly, that every point on the balloon is the center. You could also say, correctly, that no point on the balloon is the center. Both of these contradictory concepts or answers are both simultaneously true. So, distance, speed, even space itself, all of these things are relative, they're flexible. And Einstein showed us that time too flexes and flows depending on our speed, which we can't know in any absolute way. So the essence of flow is that there are no anchor points in the universe. All is in motion, all is process, all is flow, even time and space themselves. Everything began as one thing. And the center of the universe is wherever you are. Try not to let it go to your head. Now, in the past, my spiritual life was about certainty. I wanted to find truth with a capital T, the answer to life, the universe, and everything. But now my spirituality is about experiencing reality in all of its forms as an inherently mysterious process of unfolding that I get to be part of for a while. Get a chance to plant some evening primroses, do it. They're an amazing, amazing plant. Third candle, stardust. At the beginning of time, when we were still in the singularity together, there was only energy. There were no atoms, no matter, no mass, no space even. No solids, liquids, gases, none of that stuff. Nothing that we would call a thing. Just pure energy. Now, matter and energy are like nouns and verbs. Matter is stuff, things, objects. Energy is movement, action, ability. So, how did the universe make all this stuff if all it had to work with was bright light? Well, at extreme energy densities, matter can actually condense from bright light. And in the first moments after time began, particles that would later form atoms of hydrogen and helium were created out of extremely bright light. Now, in a normal lecture about the history of the universe, you would just move on to what happened next. But let's pause for a second. This is something from nothing. Nouns made from verbs. Energy is not exactly nothing, but it's not a thing either. It's not an object. It's an ability. This is like squeezing diamonds out of smoke. It's a miracle. It's a scientifically described miracle, but it's no less miraculous just because we know that it happened and how it happened. So the early universe had hydrogen and helium atoms. Great. Now what? Look around this room. Is there anything in this room you can make if all you have in the pantry is hydrogen and helium? You can't even make water if that's all you have. So where did all this other stuff come from? Well, making heavier atoms from light ones requires really high temperatures, like those found inside our sun. If they're moving fast enough at a high enough temperature, two hydrogen nuclei will crash together and stick, creating helium. That's called fusion. Then another hydrogen can crash into the helium, creating lithium, and so on, building heavier and heavier atoms, heavier nuclei. Lithium, carbon, fluorine, and so on. Larger atoms up to iron. But normal stars like our sun can't make anything heavier than iron. And anything they do create is just going to sit there inside the star forever. It's not going to be available for making planets, for example. So none of this stuff that we interact with every day came from normal stars like the sun. But there are some stars, some very rare supermassive stars. They're called supernova stars. They have to be at least 10 times the mass of our sun to do this. At the end of their fusible life, they get kind of hollowed out. And at some point, they implode. Everything in the star falls towards the center of the star. And then they collide there at the center and explode again massively outward. And just in the moments of that implosion and explosion, the temperatures are high enough to fuse or create all the other elements that we find on the periodic table, the natural elements. So, but then they spew it out into the surrounding space as hot dust that's available to come together very slowly over millions of years by gravity to get pulled together into new solar systems and new planets. So near here, somewhere in our region of this galaxy, about 9 billion years ago, a supernova star exploded, created, and then made available all the stuff that makes up the Earth and the other planets of our solar system. You could say that star's death gave us life. Now you might be wondering, how much energy are we talking about? Well, if you converted all the matter in your body back to energy all at once, it would be the equivalent amount of energy as a lot. It's just a lot of energy. So a huge amount of energy was compacted to make the atoms in your body. And it's the same blazing white light energy that exploded into existence at the beginning of time. The essence of this stardust candle is that your body and everything else is a condensed form of bright light, and lots of it. Energy explosively forged into matter at the beginning of time, and then built in the furnaces of dying stars into heavy atoms. You are the universe, made of itself, but now aware of itself. The spiritual implication of this, for me, is that the seeds of you and me were present at the dawn of time. And we are descended from stars just like those that we see in the night sky. Talk about noble blood. This body is just one stage of our long, sacred journey together. Fourth candle, nothing. So, we're made of atoms that were constructed in supernovas. What do you know about atoms? You might be picturing something like this, which is very nice for chemistry. You've got a nucleus with protons and neutrons in the center, a bunch of electrons zipping around the outside. It works really well in some applications, but it's a gross oversimplification. Atoms are not really like this. So to get a better handle on it, let's start with the simplest atom, hydrogen. Hydrogen has one proton in the nucleus and one electron zipping around the outside. So if we scale that up so that the proton is like a cannonball, a shot put, it's a solid chunk of iron about the size of a grapefruit. At that scale, the electron is the size of a BB, but it's doing that zipping around a mile away in our hydrogen atom. So if we apply that same scale to an atom of iron, for example, you might want to picture 56 cannonballs in a pile here on the floor. And about a mile away, there are 2 BBs zipping around. 2 miles away, 8 more BBs. 3 miles away, 16 more BBs. Can you see them? Pretty small, pretty far. About 7 miles away in several different directions are the next nuclei, the adjacent, like the neighboring atom, its nucleus is another pile of 56 cannonballs sitting on the floor about 7 miles away. What is between this pile of cannonballs and the one 7 miles away besides those BBs zipping around?
Nothing.
Nothing. Empty space. Even solid iron is mostly empty space. But I misled you by showing you pictures of cannonballs and BBs because these subatomic particles are not things. They're phenomena. They're events that sometimes act like things, but they are not things. Let me show you. This is a classic quantum physics experiment. You take something opaque, like a thin piece of aluminum foil or gold foil or something like that, and you make a very narrow slit in it with something sharp, like a razor blade. Very thin slit. And then you shine a laser beam on it. And you might expect that what you would get on the opposite wall would be a bright laser spot. But that's not what happens. If you make the slit narrow enough, the laser beam, the light diffracts or bends around the edges of the slit and goes out in all directions. So the brightest region is directly opposite the laser beam. But then it gradually dims off towards the edges of the screen. And no matter how wide you make the screen, some light still hits the very edges because it's going out in every direction. You see that? You follow that? All right. This makes complete sense if we're talking about light, because we know light has wave properties. You can do this in the bathtub. Water waves will do this. Sound waves do this. All kinds of waves diffract around the edges of a slit. But let's make things a little more interesting and put two slits next to each other. Now, the light bends or diffracts around the edges of both slits, but now you've got light going out from two sources, and it interferes with itself. So, for example, any place where two crests of a wave meet, you get bright light. Two troughs, bright light. But any region of space where a crest and a trough get superimposed on one another, they cancel each other out and make darkness. So you might expect two bright laser spots on the screen. But what you get is alternating bands of light and dark, where the interference is constructive or destructive. And again, no matter how wide you make the screen, some light in those alternating bands will still hit the very edges of the screen. Now again, if we're talking about waves, this makes sense. Waves do this. But let's replace our laser beam with a beam of electrons, or a beam of protons, or a beam of neutrons. When we do that, the same thing happens. Physicists have even been able to shoot one single electron at a double slit. The electron goes through both slits simultaneously, interferes with itself, and makes this same pattern on the screen. They can't be little balls. They can't be little BB-like things. There's something much more mysterious than that. The same thing happens with protons and neutrons too, which make up all atoms. All this stuff is made of protons, neutrons, and electrons, and they all do this. Now, I barely scratched the surface of modern physics. It gets weirder. It gets a lot weirder. But the essence of nothing is the things we think are most real, most tangible, most solid are by their nature more like phenomena, stories, processes, energy. Matter, even now, is made of verbs, not nouns. I was raised in a New Age family, and I know that pop culture paints New Agers as some kind of hippie yoga space cadet saying things like, I am a being of light. And, they can smirk, but it's true in a hard-nosed scientific kind of way. We are beings made of light. So how would our spiritual lives be different if we experienced ourselves not as objects, but as a wild dance of ancient and mysterious energy? White light made into flesh and blood. Fifth candle, evolution. Evolution is both a process and a history, and the process is fairly simple. Darwin's insight just had 4 tenets to it. The first is that there are more offspring born in each generation than will live to have offspring of their own. The second is that those offspring are not all clones of one another. They vary. They're a little different. Those variations are heritable. If it's not obvious, this is my daughter. So we're not clones of our siblings or of our parents, but we do share some traits. Those variations get passed on to our own offspring. Since we know that not all of the offspring will make it to have offspring of their own, some of those inherited variations will bestow an advantage in the environment, and others a disadvantage. The ones that provide an advantage will in turn get passed on to more offspring than the ones that are a disadvantage. Disadvantaged traits bring fewer offspring just because they're disadvantageous. So if you apply this over many generations, you would expect, for example, that if there's some advantage for a horse being larger than other horses, that horses would get larger over time. And that's exactly what we find in the fossil record. Horses used to be the size of house cats, raccoons, and now they're big enough to ride on and pull beer trucks around. So shorter generations makes for faster evolutionary change. Right now, our skin, yours too, is covered with Staph aureus bacteria. Don't freak out, it's a good thing. Staph aureus help protect our skin from pathogens. But if you expose Staph aureus to dilute or intermittent antibiotics, in just a matter of weeks, they can evolve into something more like MRSA, methicillin-resistant Staph aureus, which if it gets in your bloodstream can be deadly. So what does this mean for us? Well, we're here because our ancestors survived to produce us. And they survived because they had what it took at the time. Traits which they then passed on to us. Those traits, all of them, make us who we are. Even the ones we don't necessarily appreciate about ourselves. So what are your icky traits? Vanity, lust, rage, ambition, addictions, jealousy. Maybe some of these sound like sin to you. Well, whatever you call them, these are traits that our ancestors needed to live long enough to make our existence possible. And if they're not suited for our current environment, let's learn to control and manage them. But what if we began that process with gratitude instead of shame? There's another implication for us here with evolution, having to do with death. We are programmed to avoid death ourselves and to grieve the death of our loved ones. But consider that the flip side of our ancestors' survival is the necessary death of our evolutionary aunts and uncles, like the dinosaurs. We wouldn't be here if they hadn't made way for us by dying. We too will someday make way for something new by dying. We live by eating, which necessarily means killing. Even when a vegan bites into a fresh apple, the cells of that apple are alive till you ruthlessly slaughter them with your pointy teeth. Does this make us horrible, vicious predators? I think it just means that life and death are inseparably connected. Stars die, and their ashes form new planets, new solar systems. Plants and animals die, and their bodies make us. Endings are also beginnings. Death is necessary. And from a really big picture point of view, I would say that death is beautiful because it's an essential ingredient of life. I'm not going to go into the story of evolution in very much depth because you can see it on the Discovery Channel and there are lots of other places to touch on that story. But I do want to just mention 4 most significant milestones in that story. And I do this because there's a misconception out there that evolution is only about competition and survival of the fittest. And those are parts of it. But I hope you'll also see that some of the biggest leaps forward in complexity have come about as a result of profound cooperation. So the first such milestone is the beginning of life itself. Somehow, atoms and molecules got assembled in cooperative arrangements and became alive. Living things made from non-living things. It's a little bit like matter and energy. Let's pause for a second here and recognize that this is not an everyday occurrence. This is a wow moment in the history of the universe. Non-living matter cooperated to become alive. It's a miracle. And this one's not yet scientifically described. I hope it will be in my lifetime, but hopefully, if not in mine, some of yours. The next big milestone is that some of these early bacterial cells took up residence inside their neighbors' bodies. And we know this happened because bacteria have a cell membrane around each of them. So do you. Each of your cells has a cell membrane. But you also have membranes within membranes. You have a nucleus with your human DNA in it, the 46 chromosomes that make up your human DNA. And it has a membrane around it. But then you also have these other subcellular organelles that have membranes around them. And some of them, I want to call out the mitochondria in particular, not only have a membrane around them, but they also have their own DNA. Mitochondrial DNA in little circular chromosomes. Guess who else has circular chromosomes? Bacteria. So we know that millions of years ago, some of those early archaic bacteria somehow got inside other bacteria and struck up a cooperative arrangement. At this point, what they do in the mitochondria is they turn sugar back into energy. The mitochondria are the powerhouse of the cells in your body. Not only yours, but almost every other living thing. This is called the eukaryotic revolution, when we started having membranes within membranes. And everything except the bacteria descended from this event. The next big milestone is that some of these eukaryotic cells, single-celled organisms, began to clump together in cooperative arrangements. And this brought tremendous advantages. Multicellular creatures can have their cells specializing into tissues and organs. You can't have organs if you're a single-celled creature. Highly cooperative. Cells cooperating together in groups. And the last milestone is that some of those whole organisms, multicellular eukaryotic organisms, began to cooperate in societies. Societies that function like large single organisms. And as you can see, it's not just humans that do this. Now recently, a lot of people, myself included, have begun using the word evolution to apply not just to the history of living things on this planet, but to the entire cosmos. We would say the cosmos evolves, the universe evolves. And when we use the word this way, we see ourselves as part of a great story. A story in which energy evolves into particles, which make up atoms, that then bond into molecules, that coordinate in cells, cells which cooperate in ever larger associations of cells and organisms. We would say all of this is evolution. Do you see a pattern emerging here? As time goes by, the complexity of the most complex system in the universe increases. Now, when I see a chart like this, I always want to go right up to, what's next? What are we going to do next? What will we think of next? And statisticians have a saying about that. They say, prediction is very difficult, especially if it involves the future. But if the trend continues, we could guess that whatever comes next will involve more cooperation and whole new scales of complexity. But one thing we can be sure about is until time ends, evolution is not finished. We're not the end of any story. The essence of evolution is that we are survivors, built from blueprints slowly refined by our ancestors' continued existence. We could choose to be grateful for all our virtues and our vices because they made our births possible. And in the continuing evolutionary process, death is a gift from the past that we will each, in our turn, pay forward to new generations. Like many people, I inherited some serious guilt and shame from my Western culture, along with some pretty twisted notions about cooperation and competition, never mind the entire topics of sexuality and death. Today, my spirituality involves trying to see sin and shame and birth and death from a deep time perspective, or, if you will, from a God's eye view. Sixth candle, emergence. So here we are in the middle of the cosmic story, but who's we? What do we mean when we say we? What do I mean when I say I? Are we just collections of atoms operating according to the laws of physics? Are we just soups of molecules bonding and unbonding according to the laws of chemistry? Are we just colonies of cells, like corals, each cell trying to live out its own destiny and survive on its own? Well, the answer to each of those questions would be yes, except for one word. We are made of cells, which are made of molecules, which are made of atoms, but there's nothing simple or obvious about any of that. Something made from nothing, molecules orchestrating their own replication in DNA and chromosomes, trillions of amoebas cooperating to play the guitar or the saxophone. Well, yeah, sort of, but no sax player emerges unless the cells and the molecules and the atoms, each a miracle in its own right just for existing in this universe. You don't get the musician unless all of those are assembled in a very particular and precise arrangement. And then, suddenly, the whole is greater than the sum of the parts. Another miracle. Similarly, a pile of steel and plastic isn't going to roar off into the sunset with you unless the steel and plastic are shaped and assembled just so. And a car doesn't assemble itself. You did. And a human body is far more complex than a car. And it brings with it uniquely human emergent properties like poetry, logic, and faith. Emergence happens when new scales of complexity give rise to new properties that were not possible before you had that degree of complexity. So, for example, some hydrogen and oxygen atoms share electrons and make possible oceans and rivers and clouds. Couldn't have that before molecules. Some cells cooperate together, and before long you have senses and flight and sexuality, consciousness. Some primates start living in groups together, and soon there emerge language, culture, morality, governance, religion, and technology. At each transition, there's three principles operating. Cooperation provides a competitive advantage. Simple things come together to make more complex things. And then new properties can emerge that were not even possible before. The whole is greater than the sum of its parts. Far greater in the case of your body. Like you, the universe is self-assembling. And your body is the cutting edge of self-assembling complexity in the universe. Einstein said it like this. The essence of emergence is that cooperation and competition work together to increase complexity, and that brings new emergent properties that were previously impossible. The universe is created. For me, spiritual devotion is measured by my efforts towards a future with more cooperation and creation and less divisiveness and destruction. Spiritual devotion made simple, but not easy. Seventh candle, 1. Play with me again. Everybody take a deep breath in and hold it. And while you're holding it, think of someone who lived long ago and far away. And when you have someone in mind, you can breathe again. I'm not trying to hurt anybody here. Got someone? I wish my students were as obedient as you guys. Who were you thinking of? Anybody? Michelangelo.
Galileo.
Galileo. Gandhi. Da Vinci. All right. Well, here's why we did this. You just breathed in over 13 sextillion air molecules in one breath. But here's the thing. Over 700 million of those molecules were also at some point inside the lungs of Michelangelo and Gandhi and Da Vinci, Galileo. The same thing is true of everyone who ever lived. Every person who ever lived, every animal who ever lived, even every plant that ever lived, is in a way right here in the air of this room with us today. Some of the oxygen molecules you breathed in when you took that breath now are you, come alive as part of your body. Speaking of plants, you may recall from biology that photosynthesis allows plants to build themselves, to build their bodies out of carbon dioxide and water and energy. We make ourselves out of plants, so indirectly we are also made of carbon dioxide and water. So let's look a little closer at these two ingredients of our bodies. This is a diagram of the water cycle. You've probably seen something like this before. Water evaporates from the ocean, goes up into the atmosphere, forms clouds, which then drift over the land, and then rain or snow brings the moisture back down onto the earth, and then sooner or later again it finds its way back to a body of water. One of the things water does on its path around this cycle is be us. Some of it spends some time being ourselves. Every sip of water you take, every beverage you take, contains water molecules that were recently posing as clouds, as waterfalls, as hurricanes, glaciers, and even other living things. And they're about to be posing as you. The magic is that water comes alive when we drink it. Water comes alive when we drink it. Something similar happens with the carbon cycle, except that carbon dioxide, as it goes around its cycle, spends some time, yes, being living things, but also things like seashells and coal and limestone, concrete, it spends some time being. Some of the carbon atoms in your body right now were a fresh apple last month, and some of them were posing as gasoline in your car last winter. And now they're alive, in you, as you. The same thing is true of the nitrogen cycle and the oxygen cycle and the phosphorus cycle. All the different elements that make up our bodies have cycles. And they spend time being other things. And they spend time being us. Every year, 98% of the atoms in your body get exchanged for new ones. Your body is like a standing wave on a river. Matter moves through you, spends a little bit of time being you, and then moves on to become something else for a while. But you are not the matter that's flowing through your body. You are the pattern that organizes that matter into a form. And the edges of the pattern are quite blurry for a lot of reasons. But one reason is because other living things flow through us too and become us temporarily as they pass through. Now mostly here I'm talking about the bacteria, but other fungi and stuff flow through us as well. On and inside your body, bacteria outnumber the human cells 9-to-1. There are thousands of species living inside you, trillions of bacterial cells, all cooperating and competing with each other and with your human cells all the time. They digest our food for us. They protect our inner and outer linings. And recently, microbiologists are finding that they influence when we're hungry and thirsty. They influence our food preferences. Even our weight and our emotions are determined in large part by the species of bacteria living in and on us. So is it me who loves cheesecake, or we? This multitude that is me. Back to the mitochondria, those remnants of ancient bacteria still operating in every human cell of your body with their own DNA. Well, all of your mitochondria came from your mother, who got them from her mother, and so on, matrilineally inherited. Paleogeneticists have been able to use the well-established mutation rate of mitochondrial DNA, those little circular chromosomes in the mitochondria, to determine that every human being alive today is the descendant of one woman who lived in Eastern Africa only about 200,000 years ago. And this is National Geographic's map of how we got from Eastern Africa to populate every other continent on the planet. Every human being alive today is the great-grandchild of one woman from Eastern Africa. It doesn't matter race, gender, ethnicity, every human being has a common grandmother. So look around at the people in this room. These are your cousins. There's only one family of human beings on this planet. And it's not just people. We share half of our genes with bananas, for goodness sakes. All living things on this planet are related. We are part of a single, unbroken family tree of living things on the planet. Now, there are many more examples of our connection and our unity from science. But the bottom line here is that we cannot separate ourselves from the earth. We are the earth. The earth is giving this talk this afternoon, and the earth is sitting in those earthen chairs listening to it. We and it are us. One thing, one life, one being, one universe. The essence of one is that you are neither separate nor separable from other people, other creatures, the earth, ancient stars, or the universe itself. Indistinguishably one. You are the universe. Come alive. Recently, I've been meditating on myself as a drop of water flung from an ocean wave like these, in the air and seemingly separate from the ocean just for a moment, but always part of a process unfathomably more powerful, more ancient, and deeply mysterious. As the poet Rumi wrote, you are not a drop in the ocean. You are the entire ocean in a drop. Now, we've covered a lot of science this afternoon, so I want to go back through it and just step a little further away. So the first candle was about discerning our place in the universe. Then grasping for anchor points and finding that there aren't any. Learning the first origins of our bodies. Exploring the illusions at the heart of reality, the dreams that stuff is made of. To misquote Shakespeare. The interconnections of life and death, virtue and vice, cooperation and competition. Exploring the role of creation in a self-assembling universe. The oneness of all life, even of all things. These are spiritual considerations, yes? Science and spirituality aren't opposites. For me, they're intimate partners, inseparable and deeply in love. So as you leave here this afternoon, I hope that you will remember that you are both central and diffuse, temporary and ancient, flawed and fine-tuned, creation and creator, certainty and mystery. We are the universe, become conscious, glimpsing our vast and ancient self for the first time and wondering, what will we create next? Thank you.